Hello and welcome to our poster presentation at Digital ISC 2020. Today we're going to talk about how we optimize deep learning recommender systems on Intel CPU architectures. What is the deep learning recommender system? So this is a kind of a model framework right now open source by Facebook. The idea here is to give hardware vendors and academia a chance to study deep learning recommender systems and actually find an optimal sweet spot here. Therefore, this workload is becoming the ResNet 50 in the world of deep learning for recommendation. How is it comprised? So today, as you can see, it's a very simple system of many different components, and therefore we stress all kinds of different aspects of our computing system. So on the bottom, we see on the input side of the model, we have dense and sparse features. Whereas the dense features are fed into relatively small multi-layer perceptron, which requires computational intense operations and data parallel optimizations. Instead, the embeddings are memory intense and model parallel. So these are lookups into huge tables which can span multiple gigas, if not even terabytes of data. All of these inputs are fed into small mini batches, which are then in the interaction of are transferred from a model to a data parallel execution, which afterwards is fed into another dense model called the top multi-layer perceptron, which again is compute intense and data parallel. So as we can see, the whole data structures needed, the whole infrastructure needed here is stressing all the components. It's like running HPL and HPCG in a single benchmark. How does compute and COM interleave? So as you can see, the forward passes, we have the embedding lookup, we have the MLP, what we discussed, and now we have to wait for the all-to-all communication to finish. And then we actually perform the top MLP. So the communication in the forward pass is pretty simple, it's an all-to-all. In the backward pass, we're getting the typical things of deep learning applications because we have to reduce the gradients. So after the top MLP, we have to reduce the gradients because we did the beta parallelization. And we also have to undo the all-to-all so that we can update the corresponding embedding tables. In the end, you can see we need a lot of collective communication, which can be overlapped with some of the compute. How do we evaluate the performance in our poster? We're using a 32-node Intel Xeon Cascade Lake system. It's a top-end CPU with 28 cores and roughly 4 teraflops of FP32 compute per socket. We're using a fat tree of OPA 100 NICs. That means we have 1 NIC per socket, and they're feeding into 2 leaf switch connected by a root switch with half the bandwidth in the backbone. These are the configuration of the workloads we analyze. On a single socket, that's what we start with because we want to make sure we scale optimal performance across the cluster. You can see for Facebook small configuration, the standard benchmark, which is the default benchmark in the LIM, by doing a lot of optimization single node, especially in the embedding part in the backward phase, we can get 100x speed up. So this you can see how inefficient often codes are if you just run them in deep learning frameworks. I want to emphasize that this is completely run in PyTorch here. And for the MLPerf configuration, which uses terabyte data set, you can see we can still achieve 8x of performance. On the upper right side, we analyze the different versions of backward embedding kernels using atomics, using TSX, which is transactional memory, or arrays-free implementation. And we want to close that we can actually see that we have a very good utilization of the node on the bottom part. In terms of weak scaling, what you can see is for the small and the large problem we look at, we're getting something like 80 to 90% scaling efficiency. And for the real work-life problem, here is the MLPerf. We are still hitting something around 80 to 70% weak scaling efficiency, which is pretty good when we scale out to the full system here. It's 26 sockets. So thank you for watching our video. I hope you enjoyed the poster, and we will see you in the next year's ISC again.